Hey, everybody. So we're going to now talk about what we call continuity. And continuity is very well related to limits, which is why we get to it here. And you may have heard the phrase continuous or the term continuous or continuity before. And a common way to think about it is so being continuous or continuity is a characteristic that a function can have or not have, or can have it in places and not in other places. And a common way to think about it is thinking of the graph of a function. Can you draw it without lifting your pen, right? Which is obviously not a great mathematical definition. It's not very technical, and it's hard to prove or disprove, but it's a really great idea in thinking about what this idea is, right? I often think about it in something that I used when I was talking about limits as well. When a function does what it says it's going to do, it doesn't surprise us, and that's what continuity is about, and that's really what this phrase "without lifting your pen" is about. Does it not surprise us, right? So how could a function surprise us? All right, so here I'm going along drawing and I don't have to lift my pen. This is continuous, but if suddenly I need to jump up to another position, that's a surprise, right? If I were to look at where I was when I was drawing this, if I'm looking at this space at this point here, you'd expect the next place my pen goes to be somewhere nearby, right? That's the expectation. But sometimes things are surprising. So using this definition, in quotes, draw it without lifting your pen, this function I've drawn is continuous except for at this point where we have this jump, right? There it's discontinuous, right? Or even sometimes we have functions where we just have a hole. We have to stop and put a hole in there if for some reason we've seen functions like this that aren't defined at these spots, right? That's surprising. We're going along in this perfectly reasonable way, but all of a sudden there's a gap for some reason. Or maybe our function, as it approaches some point, shoots off towards infinity, right? Or maybe from the other direction it's shooting off, right? We've got these asymptotes where we're not defined. That's a surprising thing for a function to do, right? We're moving along and we suddenly can't get across this line. We just have to keep going up and then jump across if we want to keep drawing it. So how do we relate this to limits? Well, it turns out to be pretty simple. So if we want to define, we're going to start with continuous at a point, right? So right now, what I would say for this first drawing where I have this gap that I use this blue line to designate, that function is continuous at all of its points at every input value except for that place. And then we'll talk about continuous over intervals in a moment. We will say a function f of x is continuous at, let's say at this point A, so at the value A, at x equals A, if and only if the limit as x goes to A of f of x is equal to f of A. Okay, so let's pick through this. First of all, it's an if and only if. What that means is if I tell you a function f is continuous at some point A, then let's write it this way. If f is continuous at x equals A, and then I also have the statement that the limit as x goes to A of f of x equals f of A, right? We can symbolically represent that if and if only if with a two-way arrow, right? Because what this means is if I tell you a function is continuous at x equals a, it must be the case that the limit at that point is just the value of the function at that point. And in the other direction, if the limit of the function at that point is just the value of the function, then it's the case that the function's continuous. So this is our definition of continuous at a point. Okay, so this means three things, right? There are three things implied in this statement, and then we'll look at some examples. This implies that f of a is defined, right? That we can't have it equal to f of a if f of a is not defined. So a function has to be defined at that point. Notice in these two examples over here, the function is not defined. We have a hole there. There's our discontinuity, or at an asymptote, a function is not defined at that point, right? So we don't satisfy this, right? Those are points where we're not continuous. It also implies the limit as x goes to a of f of x exists, right? It has to exist. The limit has to exist, otherwise it can't be equal to something, right? Notice here, where there's this jump, the limit as x goes to a of f of x does not exist. We can see from the drawing that the limit from the left and the limit from the right are not the same, and so the limit doesn't exist. So how can it be equal to the value of the function, right? So these two things are implied in the statement, and then, of course, then we also have to have that the limit as x goes to a of f of x is equal to the function there, right? So that third statement implies the first two, right? So these are like the three pieces you need for continuous at a point. Our functions defined. If your function is not defined there, you don't have to think about continuity. It's something that only exists for the function defined. If it doesn't have a limit, you don't have to think about continuity because we need the limit, and then you can check, do these two things equal each other, right? So let's look at this one where I have, well, something similar. Suppose I have something like the one I drew above where we have a hole, but instead of a hole, we just have the function defined somewhere else, right? So these two cases up here, I'll mark them 1 and 2, were cases where the function doesn't exist. That's why we didn't have continuity. This case 3 was a case where the limit didn't exist, so we couldn't have continuity. Here we have the case where the limit does exist, right? The limit is whatever y value this hole has, right? The function's going towards that hole, but the function value is something else, right? So this is our limit as x goes to a of f of x, but the y value up here is what f of a is. So they both exist, but they don't match. These are three ways continuity can break. When we don't have continuous, when this is not true, f of x is discontinuous at x equals a. Okay. Now, in all 4 of these cases that I've drawn here, at the other points I've drawn, we have continuity, right? If I pick some random point right here, this is the limit as x goes to whatever value this is at that point, but it's also the value of the function. They're the same thing, right? What the function looks like it's going to do, it does, and so it's continuous. And any of these points here, that would be true. Okay, so this is how that notion, draw it without lifting your pen, helps us, right? It's very easy to then decide when we have these nice smooth drawings that don't do anything super surprising. And maybe I can say better what surprising means. When we're at a point nearby, we can kind of guess what the next point's going to be, right? If I'm drawing this, if I'm drawing some function and I stop right here, if you had to guess where the next point was going to be or the next set of points, you can draw a circle maybe and say they're probably going to be somewhere in here, right? And even if my function starts going way up or way down or continues on the path it's going, right? All the different paths we could take would start somewhere in that circle, right? Some would go somewhere else nearby. But if we're discontinuous, we could be anywhere. I can jump all the way down here and continue on my way, right? Okay, so let's do some more examples. Talk a little more about continuity. Here's a big idea, a very helpful idea. One of the facts that we talked about when we were discussing the limit laws in some previous videos is that if f of x is a polynomial or a rational function, then, and A is in the domain of f, then the limit as x goes to a of f of x is equal to f of a, right? We showed this using the limit laws in one of the earlier videos, right? This statement can now be restated just a little bit differently by saying that polynomial and rational functions are continuous on their entire domains, right? Because this just tells us that it satisfies the definition of continuity at each point, right? So that's what I mean by the entire domain, meaning at each point in their domain, rational functions and polynomial functions are continuous. For polynomial functions whose domains, unless there's some real world constraint, their domains are everywhere. So polynomial functions are continuous at every point. Rational functions are continuous on their entire domains as well. Sometimes rational functions have holes in their domains, either just a hole, a gap, or an asymptote. But in either of those cases, they're not continuous at those points, but they're still continuous at every point in their domain because those points are not in their domain. So wherever they explode into positive or negative infinity or have a hole, they're not continuous because they're not even defined there, but they're continuous everywhere else. Okay, so this is great. We don't need to spend any time thinking about whether polynomials or rational functions are continuous at points. If it's in their domain, they are, and we can just state that and move on. Okay, let's look at another function. We talked about the function we saw in the previous video, maybe 2 videos ago, that the limit as x goes to 0, and the sine of x over x is equal to 1. Okay, so we showed that last time. So if I define the function sine of x over x, if I let f of x equal sine of x over x, notice this function is not defined at 0. Okay, it's not defined at 0. So it fails to be continuous. So is discontinuous at x equals 0. It's not defined there. It can't be continuous. But it's discontinuous in a particular way. Okay, so I'm not going to prove this right now, but let's consider that our knowledge of sine of x, right? So if we think about the definition, let's prove this lightly. No, we won't go down that road. Sine, if you think about the graph of it, right? You can draw this graph, this undulating right? It has this periodic nature that I'm capturing as best I can, right? And it goes on like this forever in both directions. This is a continuous function. It's continuous over its whole domain. And we're dividing it by something continuous. And it turns out that this will be continuous everywhere except where x is equal to 0. Okay, let's look at a graph of this. Here's what this graph looks like. Let me zoom out a little bit. Right, so we still get these waves, but because it's being divided by x, those waves are getting smaller and smaller. But let's look closely at as we're approaching 0, right? We've got this hole in our function at 0, 1. The limit is 1, but the function is not defined there, so it's discontinuous. However, let's let g of x equal, we'll do a multi-part function. Well, let's let it equal f of x, so it's the same as f of x if x is not equal to 0. So it's the same function as f everywhere but 0. And then we'll let g of x equal 1 if x is equal to 0. What have we done to this function? We've plugged in that hole, right? Because now, even though the sine of x over x can't handle that part, we've told our function, well, when you put in 0, when that f of x fails, just spit out the value 1. Now it's certainly the case that the limit as x goes to 0 of g of x is, it's doing exactly the same thing as f of x, right? Remember, the limit doesn't care about what happens at 0, it cares about what happens near 0, so it's doing the same thing as f of x, so its limit is the same as the limit of f of x, which we know to be 1. And that happens to be the value of g of 0. And so the limit is equal to the value there. And so we've fixed that discontinuity. This function is now continuous at that point, and it turns out it's continuous everywhere, right? So this kind of a continuity where we have a hole where the limit exists, but we have a hole that we could repair. We call that a removable discontinuity. Movable discontinuity. Okay. We have a removable discontinuity when the limit as x goes to a of f of x equals some number. Okay. If the limit exists, then we can fix our function, right? Because if the limit exists, what it means is you have to have this kind of situation where there's a hole, and all you'd have to do is define the function to be equal to that value there, right? Maybe the function is defined to be something else there. Maybe it's not defined at all, like the case we just did, but you can redefine it to fill in that hole, right? This doesn't work, right, if there's some kind of a jump, because how do you fix this without changing the rest of the function? You can't just pick one point and fill it in. You'd have to move this line down, right? Or even worse, when we have an asymptote, right? How do you fix this? Because, right, they're doing very crazy things there. We have names for those kinds of discontinuities. So let's talk about jump discontinuities. These are when the limit as x goes to a from below exists. So let's say it equals L, and the limit as x goes to a from above exists. We'll call it M, but these two limits are not equal. right? So that's what's happening in this picture here. From below, we're approaching one value. From above, we're approaching another. Or here's a classic example of this kind of discontinuity, a jump discontinuity. Let me change my, let's go. Oops. Okay, there's our step function. This is the ceiling function, the function that returns the next smallest integer from any number, right? So if you put in a value between 0 and 1, it returns 1. It goes up to the first integer it hits, right? That's another way we could say it. So at each of these points where we have this, well, this jump, right? The limit from above goes up to one value. So in this case, if I was looking at the limit as x goes to 1, from above, let's just write it, the limit as x goes to 1 from above of, we'll call it ceiling function of x is equal to 2, and the limit as x goes to 1 from below of the ceiling function of x is equal to 1, right? From below, we're at 1, from above, we're at 2. Those two don't match, and so we have this jump discontinuity. Okay, so that's another discontinuity we can have. And then finally, we can have an infinite discontinuity. And we have that if the limit as x goes to a from above of f of x equals plus or minus infinity, or the limit as x goes to a from below of f of x goes to plus or minus infinity. Remember, this means that the limit doesn't exist, but that we can make the function as large in either the positive or negative direction as we want. And so a classic example of this, clear this drawing. Here's a, oops, there we go. This is 1 over x minus 2, right? It has this asymptote at 2 where it explodes off into positive and negative infinity, depending on which side you're coming from. And then we have an infinite discontinuity, right? So the jump in infinite discontinuities, you can't really fix, right? In some sense, you could say these discontinuities are getting worse. A removable discontinuity is barely a problem. You can redefine the function at a point or maybe several points. Jump discontinuities, you'd have to make some pretty major repairs to a function, right? Maybe you pull that line down. It still maybe looks somewhat the same, but it's a very different function. And then, of course, to change an infinite discontinuity, you're really changing the entire nature of a function if you get rid of that kind of a discontinuity. Okay, so moving on. Let's go back to thinking about these jump discontinuities for a second. Do a little drawing here. So let's just look at a little piece of that ceiling function. So let's say I'm looking at the piece. So let's make this the point 1, 1, and this will be the point 1, 2. Right, so I'm looking at that place where we go from 1 to 2. Now, when we talk about continuity, we're talking about the function not being surprising in some sense, right? Doing things we don't expect it to do. Sometimes we only care about looking at it from one direction. In other words, we can look at one-sided continuity, right? And there's no big change here. Remember, we said continuous is when a function is equal to its limit. Well, we can say a function is continuous from below or the left, however you want to say it, right? If the limit as x goes to a from below of f of x equals a, or we can say continuous from above or from the right if the limit as x goes to a from above of f of x is equal to, oops, I wrote a above, that should be f of a, sorry. F of a. So in this example here, this function, if this is f of x, we could say f of x is continuous at, oh, both of these, sorry, should have been at x equals a. At x equals a. F of x is continuous at continuous from below at x equals 1, and f of x is discontinuous at x equals 1, right? So I just want to make this distinction. It's continuous from below at 1. It's discontinuous from above, which also means it's discontinuous overall, because if it's discontinuous in either direction, it's discontinuous overall, right? So if we only care about from below here, we would say it's we can say that it's continuous from below at x equals 1. It's discontinuous when we come from the other side, so it's discontinuous overall, okay? Also, this function is continuous at every other point that I've drawn here, right? At each of these jumps of these step functions, let's look at that picture again, right? At each of these places where it jumps, it's discontinuous. It's continuous everywhere else. And so we'll often talk about the intervals on which it's continuous. We'll say that f of x is continuous on the interval AB if it is continuous at all values of x, let's say, in this interval. Okay. We'll also sometimes talk about closed intervals. So I might say f of x is continuous on the interval AB if it is continuous at all points or all values of x in the open interval AB and continuous from below at B and continuous from above at A. Right? So we'll use the symbols and say f of x is continuous on the interval, but if we use the closed symbols, it's implied, because at a closed interval, we're only talking about from one direction, that the continuity at the endpoints is one-sided continuity. We can also do similar, right, if we have intervals like this or like this, where we would mean it's continuous. If we said it's continuous in one of these intervals, it's continuous at all the points on the interior, all the points in the open interval AB, but it's continuous, say in that first example, from below at B, or it's continuous from above at A in the second example, right? So this graph we have up right now, the ceiling function, for instance, I could write is continuous on the interval. Let's just look at this one that goes from 0 to 1, right? That's looking, I'm just looking at this piece right now, right? So at 0, it's not continuous because as it approaches from above, the value of the function is not 1 where this dot is at, right? This dot is at 0, 1. But as it approaches the endpoint from below, the limit is 1 and the value is 1, right? So it's continuous on that interval. And what we mean is it's continuous for all points, continuous for all points in 0, 1, and continuous from below at 1, okay? And in fact, we could say this function, this is just one interval on which is continuous. We could say this function, the ceiling function is continuous on all intervals, let's say n to n plus 1, where n is an integer. Okay, right? So this is all these intervals as we go in both directions, right? 1, 2, where it's closed on the one side, sorry, open on the one side, closed on the 2 side. And then the interval 2, 3, and so on, and going backwards, the one we just did, even going into the negatives. All right, so extending both directions forever, we get continuity like that. Okay, let's do one last example. Let's look at a rational function since we were talking about them earlier. All right, so what we want to find the intervals where g of x is equal to x to the 5th plus 7 over x cubed minus 3x, right? Well, we've said that rational functions are continuous on their domain, so finding out the intervals where this is continuous is simply finding out what its domain is. And a rational function is defined wherever the denominator is not equal to 0. So we need to find out, where is this equal to 0? Well, that's when we can factor out an x, we get x squared minus 3. We can use difference of squares equals 0. So this is equal to 0 if x is equal to 0, x is equal to root 3, or x is equal to negative root 3. So the domain is simply where these are not true, right, at all other points. And so we can say our function is continuous on, let's use interval notation, from negative infinity to negative root 3, then between negative root 3 and 0, then 0 and root 3. Oops, not a comma, we want a union. And then root 3 to infinity. So on all these intervals, this function is continuous. At those points in between the intervals, it is not. So let's finish with a picture. Let's get rid of my notes. All right, so here is, let's get a nicer picture. Maybe I'll squeeze in a little bit. even more. Okay, good enough. There's our rational function. So let's get rid of these asymptotes, right? It's got a pretty odd shape to it, but it's continuous everywhere except where those 3 asymptotes are, right? In between them, every other point, the limit at that point is equal to the value of the function at that point, right? Between those asymptotes, you can draw any section of this graph without picking up your pen. If you have to cross the asymptote, then you would have to pick up your pen. Okay, let's finish there. That's it for this one. Thanks, everybody. I will see you next time.